everyone, welcome to our first webinar of 2025. My name is Anya and I'm responsible for business development at K-Mine. And before we dive in, I'd like to remind you to follow our LinkedIn page for updates on our latest news and upcoming webinars. And I thank you all for joining us today. In our webinar today, we will focus on determining and justifying the optimal pushback number and what kind of economic impact does it have. We'll explore how to calculate the best pushback strategies and discuss their economic implications. Also, later today, we'll be joined by Dr. Bright Afam, who teaches at various universities, and he will share his insights and expertise on creating pushbacks. Let me introduce you to K-Mine first. Founded in 1994 in Ukraine, we've now extended our reach to Europe, United States, and Canada. And our team consists of diverse professionals, including developers, geologists, mining engineers, with many people certified in NI 43-101 and JORC reporting standards. And we serve a broad spectrum of clients from small exploration teams to large corporations, always focusing on delivering high-quality and cost-effective solutions. At K-Mine, our primary focus is our software, and it's designed specifically for the mining sector to support every stage of a mining project, from initial exploration to full-scale production. Our software consists of 12 modules that cater to both open pit and underground mining environments, and the uniqueness of our solution lies in its adaptability. Whether you run a small operation or a large corporation, you can choose the models that match your specific operational requirements, and it can be just one module or the entire set. These models cover all essential areas from geological data management and surveying to creating optimized mining plans for both current and future endeavors. With capabilities to integrate IoT devices or dispatch systems, our software ensures real-time monitoring. But our solution stems from real-world industry experience. It's designed to address the challenges that we've encountered in our consultancy work. As I mentioned previously, our team includes qualified persons who deliver reports in compliance with NI 43-101, SK 1300, and JORC standards tailored for different project stages like pre-feasibility study, feasibility, mineral resource estimation, preliminary economic assessment, and others. We have extensive expertise across a wide range of hard rock commodities, including critical minerals. And if you'd like to explore how our services can benefit your project, feel free to leave a comment below or reach out through our contact form on our website. So let's briefly outline today's discussion. We'll begin with the fundamentals: what pushbacks are, their purpose, how to implement them, and the rules governing their construction. From there, we'll delve into main topic today, which is the impact of the number of pushbacks. Since we software developers, will demonstrate how pushbacks are managed within our software, exploring various scenarios, and we'll also touch on automated design, which is crucial in planning. Then we'll move into scheduling, review the outcomes, and conclude the insights on whether pushbacks are necessary, their optimal configurations, and other questions. So let's begin by explaining what pushbacks are and their purpose. Although many in mine planning are familiar with them, we'll provide some insights. In today's dynamic raw material market, staying vigilant and detailed in planning is crucial. Strategic planning is the initial step, setting the stage for long-term company decisions. The primary expense for a mining company often lies in mining operations, and to secure the future, detailed plan for mine development until the deposit's depletion is essential, and this is where pushbacks come into play. Pushbacks allow for management the intensity of mining across different areas, coordinating efforts over time. A pushback represents a controlled phase of pit development, ideally made up of unique adjacent volumes that can be mined with the current equipment while respecting practical geometric limits. Generally, pushbacks are mined sequentially, and once overburden is removed, equipment shifts to begin the stripping in another area, ensuring timely mineral extraction. So if you're wondering why and what's the difference, we've been doing this for ages, it's been working fine. Let's compare how different mining methods impact in operations, intensity, and other factors. First, let's clarify what we mean by conventional mining. This involves progressive pit development where there isn't a clear mining front, but rather multiple mining zones influenced by specific mining conditions. Sometimes there might be a direction to the mining operations, but it wouldn't qualify as pushback due to the mining approach. With pushbacks, a cut is made to a specific width from the pit top and is mined progressively downward until reaching the maximum feasible depth. Each pushback must extend the pit's depth at its lowest point, giving the entire pit a defined direction in its development. So let's talk about how conventional mining stacks up against using pushback and how these methods impact mining operations. If you go with conventional mining without pushbacks, you get some nice benefits. For example, you have access to most of the mining phases at the same time, which means you can mix and match minerals to keep up with what the processing plant needs. That's pretty adaptable if things change around you, and you can also adjust production volumes without too much hassle. But there are downsides too. Over the life of the deposit, you're looking at the higher stripping ratio because you need to open up big areas just to get to the ore. This also means you're redesigning roads with more flat spots, which isn't great for your heavy-duty trucks, increasing how far they have to travel. More ramps mean less productivity, more restrictions of building them, and all adding up to higher cost for each unit of what you produce. Now, if we switch gears to mining with pushbacks, it's a whole different story. You're looking at lower cost and better productivity for your equipment, which means you don't need as many machines. The current stripping ratio is way lower than with conventional methods, making things more efficient. Planning becomes clearer and more predictable, which translates to cost savings and higher profits over time, boosting your NPV and making your project more attractive to investors. However, of course, it's not all sunshines and rainbows. If you need to switch from one method to another, you might have to give up some production volumes to do more work to open up new mining areas. And if you're too conservative with the size of your pushbacks, you might find yourself short on raw materials if you suddenly need to increase processing rates, requiring some extra planning or adaptation. So while pushbacks can streamline and optimize your mining operations, they come with their own set of challenges that you need to be ready for. So when we talk about pushback, there are some rules you have to follow when you're setting them up and building them out. First of all, each pushback needs to be made of unique connected blocks. This is a key for planning pit roads, maintaining safe slope angles on the pit walls, and each new pushback should connect to the previous one, sharing transport links. Then you got to tailor the pushback to the equipment you're using. Before you even start planning, you need to know exactly what machinery will be in play, from mining to loading and transport. This ensures that your equipment can operate at its best within the pushback. Third, each pushback should have enough of the right quality minerals to keep the processing plant running while you're opening up the next pushback. These rules also bring some limitations. Your pushback has to be manageable with the equipment you have. It needs to connect properly with neighboring pushbacks, and it must meet the plant's needs in terms of both quality and quantity while it's being mined out. So let's take a little trip back in time to see where pushbacks in open mining just came from. The idea of pushbacks really took off with the growth of mine development planning, especially in those massive quarries where managing resources efficiently and cutting costs was the key. Now, in the early days, it all started because people realized they needed a smarter way to use space in mine development. And you start seeing the term pushbacks in technical reports and research around 40s, 50s, when quarries were getting bigger and there was a push to optimize everything. Then in the 60s and 70s, pushbacks became more popular thanks to new computer technologies, and this allowed for modeling different planning scenarios considering all sorts of variables like geology, mining conditions, and how much you're producing. This was also when powerful software started popping up, which really helped with planning, including how to develop pushbacks. It was around this time when we started using mathematical models to fine-tune pit planning. Understanding how materials behave and being able to predict it accurately meant that pushbacks became a go-to method for big mining companies like Rio Tinto and BHP, who were at the forefront of adopting these technologies. Fast forward to now, and pushbacks are all about the high tech and complexity. With the advent of computer technology and geographic information systems, we can plan even with more precision and efficiency. So the evolution of pushbacks has gone hand to hand with advancement of mining engineering, tech, computing, and making it essential part of strategic planning in the mining industry today. So let's check out some examples that really make a case for using pushbacks in mining. Back in the 70s at the Morenci copper mine in Arizona, they started using pushbacks for smarter mine planning. It was one of the first big projects to put this method to work in managing a large open mine. They managed to lower the cost of moving materials around and reduce losses while developing the mine. By planning each pushback with geological details in mind, they not only cut operating costs, but also ramped up productivity. Plus, because everything was so well coordinated, there was less downtime for equipment since they could use it to its full potential. Then there is a Rio Tinto case, a major player, of course, in the mining game, using pushbacks in their operations across Australia, Canada, and Mongolia. And for example, in the Pueblo Viejo region in the Dominican Republic, pushbacks have significantly upped the efficiency of their large open mines. They mine different materials at different times based on their geological properties, which reduces processing costs. This has led to substantial savings through better logistics and resource management, but not to mention lower transport and processing expenses. BHP, another giant in mining, employs what they call the wave method in the Australian iron method mines, especially in Western Australia. Using pushbacks here has allowed them to get the most out of the mines by mining in stages, each optimized for economic efficiency. And this approach has lowered energy costs, made material transportation more efficient, decreased harmful emissions, and it also given them stable production rate, reducing the risk of big financial hits if market prices for metal products swing. Advanced computer models have helped them forecast production and cost more accurately, which has been great for their bottom line. These cases show how pushbacks can transform mining operations, making them more efficient, cost-effective, and environmentally friendly. So once you've made the call to design a pushback, what are the big questions you need to tackle? First of all, how many pushbacks do you need to keep the pit running smoothly? The number depends on the wave parameters you're working with. Then you've got to decide how wide should each pushback be, how long, at what depth should the pit go, how do you hit the sweet spot between the stripping ratio and keep mining consistent, and how long will it take to access mineral in each pushback. These are just some of the questions we're going to try to answer. And now joining us, a mining consultant and a professor at University of Mines and Technology in Ghana, and also assistant professor at Queen's University in Canada, Dr. Bright Afam. Bright, nice to see you, and happy that you found the time to join us.
Yes, thank you very much. Nice to see you again, Anya. Yeah.
So talking about pushbacks and how effective they are, what do you think about it, like in your personal work, and what do you think are the key elements of effective pushback?
All right. So in talking about pushback, I think we should also mention cutback. So pushback and cutback, they're actually different, but we use them interchangeably. The pushback refers to expanding the pit or getting more areas outside the pit into the pit, but following or using the already existing, you know, peripheral parameters like the beam height, the beam weight. You maintain everything and you push it back. But in cutback, it's the same thing, but you have the flexibility of changing the parameters. And therefore the name applies as cutback, where we change the parameters, or if the parameters change, we should refer to it as cutback. If not, pushback. And because I teach students, I'm always particular about the terminologies. So pushback itself is very important element in mind planning, and the key element that needs to be considered are some of the variables that would ensure effective pushback creation in surface mining. And basically, you want to balance the technicality, the economic, the environment, and also the operational factors so that you can have an optimal pushback. So in doing that, what you need to consider firstly is the geotechnical stability of the new area that is coming into the pit, whether the slope angles needs to be maintained or varied, whether the geology is changing within the space or area where we are extending to, and therefore it will affect the beam configurations and even the bench configurations. Those are very important. Another critical important which the industry um, uses a lot to affect pushbacks creation is the economic optimization. So you first want to know that you are making profits when you bring that portion of formation into the pit, and whether it's actually maximizing the net present value or you are just satisfying the community or the country by just creating jobs, so just increasing the life of mine. So that's very important. Then what I love, the third one is the consideration of the grade requirement for the plant. And that's what most people miss, or we don't particularly pay attention to that, whether the current reserves, which is coming into the strategic plan, has the right grade, whether the grade is going to improve the plant. So there is the need to, model the plant's requirement in terms of the grade that is coming into the pit. That's right. So these three are key. And the fourth one, very important, is the equipment and operational constraints. So basically, we are looking at an area which is constrained. The area is basically relatively small, or the mining weight is very limited. And therefore, you want to ask yourself whether you are going to continue to employ your current equipment layout, or whether you need smaller equipment, whether a new ramp will suit the type of equipment you are using, or you need to bring smaller equipment to be able to harness the efficiency and effectiveness of the machines in creating that pushback. Then the risks and operational flexibility are also essential keys that needs to be considered. Are we going to have challenges when we are operating the mine. And in my field of work as a consultant, I've come across pushbacks where they were not able to operationalize the the pushback, the blasting, the blast, and it rails from the BEMS into the pits. And so they had a lot of loss in the oil reserve. There were a lot of dilutions because they have to mine the outcrop in the pushback, and because it's protruding in a small size, but they have larger equipment, they have no option than to get more waste into the ore. And so the operational flexibility needs to be, looked into when you want to consider the pushback creation. So these, I think, are a few elements that needs to be considered.
And you mentioned that there are pushbacks and cutbacks. I guess, how do you decide which one do you use?
So the nomenclature is such that if the parameters, the existing parameters that the mine has adopted is going to be maintained, then we would say that we are employing cutbacks. But if it's going to change, and the changing will based on these key elements that we are referring to. Geology is always the king in mining, and therefore your stability, safety are first thing to consider before the economic aspect, and then the operational ability. So if based on your assessment, based on your modeling, based on your design, if the parameters needs to change to ensure that you maximize your extraction, then we'll refer to it as a cutback. If not, then the nested pits that we generated around the optimal pit can just be employed, and therefore we will just say we are employing pushback.
Mm-hmm. And what's typically like missing in pushback creation process? I guess, what are the most common mistakes that they do when we talk about pushback?
Yes, this is very, very important. So when we are considering the pushback and we are looking at some of the things that they mix. So in the industry, the traditional way of developing the pushback is to, if you want to be quick and dirty, you just do a rough design. But most people would like to also quickly model the new formation that is coming into the picture. So what we do is that some people are not able to look at the long-term goal of the mine. So the pushback must sit in the long-term goal. Most traditional pushback creations focus on short-term profitability. They neglect the long-term implications, such as future phases that must come into the mining plan, or some operational bottlenecks that may come in future. So you need to integrate the operational perspective of the mine into the pushback creation, and that is mainly meshed. Then also the geological uncertainty are meshed. So the variability of the ore grade, because the ore is continuous, most mining engineers tend to quickly assume that whatever that they saw in the pits are what they will be experiencing or they will be encountering when they do the pushback. But you need to collaboratively work with other team members, the geologists, to ascertain whether the ore grade is not varying. And if it's varying, how do you include that in your global optimization? And again, that will then take also the collaborative input from the processing guys, whether the variation of ore that is coming from the pushback would be suitable for the plant? Do they need to change the operational parameters, or they need to maintain it? And so there is supposed to be that conversation across all the various departments so that everybody will understand where we are going to. And so when you look at a thing in the long term, then you get a benefit. The last one I want to mention is the commodities and the market condition fluctuations. So it's very important that as we consider pushback, we also look at what are the commodities trends. Is it in, is it the right thing to do to model the trend so we can include that? I believe in that because I love dynamic mining planning. So most traditional miners or mining engineers do not look at the trend, and therefore after 2-3 years of pushback, then they come with another decision of let's do another pushback. And so you see that the challenge and the difficulty in handling the first pushback, impacts the second or third one that needs to be created. That's right. So these are often missed.
Any innovation or in creating pushbacks that you know of, like something that was not considered before?
Yes, I think we need to incorporate the real-time data into the pushback. We need to assess the impact of future trends into the future and create strategic stockpiles to be able to handle the resource which is being depleted. So what I mean is that you know that for now, the price of the commodity is at X amount. But when you look at the trend, it's going to increase in the next 2 years, in the next 3 years. Your pushback is going to be completed in the next 5 years. Now, do you include that dynamic pricing into the pushback creation? Yes, of course, you have to do that. But most mining companies do not do that. They maintain the same rate, the same price, and therefore they lose some minerals in the ground, and in future they want to come for that. By that time, mining cost might have increased, and again, the mining weight must have reduced. So what a mining engineer needs to do is to assess the trends and see how some of the scenarios that are being created for the pushback will capture the resource depletion stockpiling approach, where the mineral may not be profitable now, but in the next year or two they may be profitable. So why don't you mine and stockpile it? If it's not going to deteriorate by the impact of the weather, then it means that you can still recover as much as you have, or you can. And also you will be able to also reduce the future cost. And I think it will be a strategic leveraging approach. The other thing too is there is the need to leverage artificial intelligence and machine learning to predict some of the geological variabilities. Currently in the mining industry, people only uses the machine learning. Majority, about 80%, uses the machine learning to evaluate the situations. But we need to move a step further because we have encountered the formation by going deep in a pit, and we now want to do the pushback. And so we have much data. How do we use that data to predict the variability in the new portion that we want to bring into the scope? And I think those are very important. Yes.
If you would kind of like try to define your personal criteria of optimal pushback, what would it be? I mean, I know that there are different criteria for that, and there are different tweaks, I guess, every mining engineer implement for his definition of optimal pushback? What is yours?
Oh, okay. So, in my experience, optimal pushback actually is derived from the nested pit shells that were generated. So usually the traditional way, some people just define or they do the pushback through designs, manual designs. But I believe that you need to model the pushback, have a system, have a tool that will be able to model the pushback and complement that with your experience. So you are complemented of the experience because the modeling in like most of the software available do not include all the variabilities or the variables that are affecting the mining, right? So when you first have your foundation or you have a layout, then you'll be able to use your experience to make it better. So in my opinion, for us to achieve an optimal pushback, you first need to model, look at the geology, its impacts, its variability, look at the strength of the rock. Is it still changing? Do we have any um, structures that are, moving into the area or that are extending into those new portions? Would they affect the formation or they will not? I have a typical example here. So due to historical blasting of a particular mine I worked, the formation was very weak. That's the hanging wall was very weak. So during the pushback creation, though the optimized area is defining a particular boundary, because of the weakness generated from progressive spontaneous blasting, you need to they needed to employ their experience to capture those areas into the pit so they will know whether it's still economically viable or not. So if they have gone straight using the various models to just define the boundary of the pushback, they would have lost some of the minerals of interest, and therefore the safety of the area will also be compromised. So you model it optimally and you also complement it with your expertise or your experience.
Any preference on using automated or manual pushback creation?
Yes. So, in my point of view, combining both, you get much value when you have the hybrid of the manual and the automated pushbacks. And I will use the automated pushbacks to uh, firstly have, the boundary, the generated pushbacks. And then I will use the manual to predefine the the constraints or use the manual to fine tune the constraints that were predefined by the automation. Because the automation one is very efficient, is fast, it's also consistent, it's scalable, it has some disadvantage because it won't accept some flexibilities, some dependencies in the inputs. We may have some challenges there. So when that is first created, then we need to complement that with the manual, which is time consuming and is subjective. Who is the one doing it, depending on the expertise of the person. But it helps to, customize and create precision around the pushbacks. You have control over the all body which is coming in or the reserve that is coming in, and it's also flexible because you can then control the geotechnical issues around it. So I always lean towards the hybrid where you combine the automation and also the manual. But I will do automation first and then fine tune it with the manual.
Is there any alternatives to the pushback approach in strategic planning? Like,
Is there any come again?
is there any alternatives like to pushback in strategic planning?
Oh, yes. So the pushback, actually, the concept is to bring in more resources or reserves into the planning. So what you could do is, number one, look at whether you want to create a satellite pit. So creating satellite pits or smaller units of pits within or around the main existing pit could be a great advantage. However, as you create a new pit, you are limited with the depth that you can go, the slopes that you can achieve. And so you want to, in your scenario analysis or in creating options, you want to check whether it is okay to go by satellite pits or it is not. The second one is to look at the mining option. Should I switch from open pits or surface mining to underground? So you want to look at whether it is okay to do a small underground within the area, usually KV methods, and you already have the existing pit. So can we drive a decline and just extract the mineral by underground methods? That's very also an alternative. Then in recent times, we are looking at robotics, mining. So usually pushbacks come with limited formation, limited areas. So we are looking at whether we have automation. You can automate the drilling, automate the loading, the hauling. So in so doing, you employ robotics, and that is also a sway or an alternative from the traditional pushback because the ground is limited. I have a friend working on, I was supporting a friend working on a project, pushback. Now they didn't consider some of these things. Now after blasting, they are not able to go back to load. So they have to now get contract mining so they can reduce the size of their trucks, the size of their loaders. Why? Because the place or the mining width is not that large. So they have to use smaller mining equipment to be able to mine all the blaster material there. So I think those are some few alternatives that we can leverage ourselves too when we want to use or go away from the traditional pushback.
Any additional hacks and interesting cases you can share with our audience in terms of strategic planning?
Yes, so I believe in resource depletion. Some of my research and publications have been on resource depletion. So there are in some jurisdiction, you are constrained to mine as much as the minerals from the ground. You are not allowed to, determine your extraction based on economics alone. They may define certain um, percentage grades or some grade levels that needs to come out. So even though it's not profitable, you still have to include it. So I believe that if the mining engineer is able to model the trends, the future trends of the commodity, the future cost, they should be able to, from start, harness the advantage of good AI or machine learning prediction tools to, create a dynamic mining strategy where they could mine for now, keep some deposits or some of the ore as low grade, not to be processed in the interim or in the short term, but they foresee that it's going to be profitable in future, and therefore they can process that. So that's very an active way of managing that. Most mining companies, most of their corporate profiles or the corporate policy is to mine, let's say, some minimum grades, or they have a threshold of price or commodity prices that they match their mining to. So, for instance, gold price is 1600 and they want to use 1200 to build the pit. I always have problem with that. The main reason is that at the current sale of the commodity is 1600. So when you create your optimized pit based on a lower value of 1200, that means that you are leaving some materials, profitable materials down there. So why don't you bring them up and stockpile the materials which are low and process those that are high that will meet the 1200 that you have set for yourself. And because this is not well defined and explained to the mining engineers or the professionals, when they use the 1200 instead of the 1600 as the pit shell, anything that fall below that, then they send the material to the waste dump.
Mm-hmm.
And therefore, a material which is of low value today but of high value tomorrow, they lose it. And usually the waste dump is such that it rails, and therefore you cannot go back to gather all the materials that you have deposited or you have dumped away or you have thrown away. So I always ask them this question: if the commodity is of low grade now, it's not making profit, but it's going to make profit in future, maybe 5 years time. You didn't stockpile that. You have used it as maybe paste, or you have mixed it with the pure waste. So non-mineralized and mineralized materials. So mining engineers need to incorporate that into their strategic plan. Again, the data-driven decision making that we make, we have AI, we have machine learning tools. Can we use that to create site-specific information where you can use that to refine your strategic plan? Those are areas that we could, take advantage on. I'm also looking at optimizing the pushback sequencing, whether there is the need to model and incorporate the future economic and technical trends. Your plants may improve, the recovery may improve in future. Have we considered that in the strategic plan? Most people do not do that. Again, most mining companies use flat rates for mineral processing, and I always have problem with that because the plant itself may be having fluctuation of recoveries. So if you use a flat value to optimize your entire mine for the entire 20 years or 15 years mine life, then when the plant is changing, you have not changed your mining extraction strategy. It stays the same, but the plant is changing, and therefore we lose value from that. So we need to unlock such values. There's also this important aspect of cross-functional teams at the early stage. So in planning, mostly the other departments, including even the environment, looking at the mine closure, they come into the planning of the mine at the latter stage. By that time, most of the decisions are irreversible. So mining companies need to have this kind of early collaboration with the other, supporting areas and include their decisions into the mine plan. I can also talk of quantifying our environmental and social considerations. In recent environmental, social governance, ESG issues, it's very important to quantify some of these considerations. And I have some good friends who have done good research on that, on how to quantify that. So most mining companies do not quantify that. They don't include that. They just use some flat rate value, and it mostly go a long way to hurt the mine. I can also talk of technological advancement. Mining companies need to stay ahead of the technological trends. What is coming up? We need to stay ahead of that. Then, what about continuous auditing? Continuous auditing. We mostly trust our colleagues to do internal auditing, but sometimes you need an external eye. You need an external auditor to give you some fair, judgment or feedback on your plan. And I think the mining companies will get much value if they have external auditors, professional auditors. So what that comes is, or what happens is that there is this value that you can create, because an experience from a brownfield may be brought into or shared with current mining professionals, and that will help them to unlock some of the potentials of the minerals in the ground, and thereby maximize the mineral extraction. So I think these few hacks will actually help improve our mining strategy going forward.
All right. Well, thank you so much, Brett. Thank you so much for your insights.
Thank you very much. And I'm happy I was able to make justice to some of the questions. So thanks for having me, Anya.
Now let's see how pushbacks are made in K-Mine software. We'll begin with the easiest way, automatic construction, where the computer does the heavy lifting for you. We've embedded some unique features into our algorithm to find the best pushbacks, considering several extra parameters. First, you need to calculate project for the ideal pit outline. Based on that, we can generate as many pushbacks as needed. For example, let's say we've made a project and where we plugged in all various data like cut-off grade, extraction rates, how stable the pit is, and the mining costs. After doing the math, we get a set of final contours adjusted by what we call the price adjustment coefficient. The report is pretty thorough, painting a near real picture of mining operations with plenty of indicators and graphs for a first look. Each set of these blocks results can be viewed on its own, allowing you to explore how volumes grow as the product price goes up. This helps in deciding the pushback development sequence, aiming to maximize NPV. For each contour, you can create a detailed wireframe, track excavation with cross-sections, and integrate geological data. For a quick analysis, we've got preset graphs that show the economic side, development timeline, rock mass removal stats for both individual and cumulative contours. And you can check this info out in different ways to get a full picture. We recommend using a coefficient of 0.95 moving forward. And in our plugin, we've set up key parameters for pushbacks like price adjustment coefficient, how many pushbacks you want, the width of the working area, minimum pushback area at both the top and the bottom, plus some other useful ones. You can also set geometric and elevational limits for automatic pushbacks or direct them, but we'll discuss combined pushbacks later. Every setting is customizable for each pushback. So now let's talk about setting up the numbers. Each pushback can have its own extraction volume and priority for different metrics. You can also add capital expenditure data to the pushbacks for a more detailed financial model. As a result, we get sets of blocks that match your desired income to varying degrees. You can create as many automatic pushback tabs as you need, allowing you to try 2 different scenarios and pick the best one for further planning. You can adjust target parameters, tech specs, number of pushbacks, and all sorts of combinations. All this can be evaluated right here without needing other software. The results can then be saved in a block model for use in other parts of software. So let's talk about the hands-on way of creating pushbacks. The big difference here is that the engineer has to think it through and set limits for pushbacks. And many engineers start with the automatic method to see the patterns, then switch to manual for crafting the most practical pushback shapes. First, you decide on the coefficient you want to work with, how many pushbacks you're aiming for, and what to do with any leftover blocks. You start by choosing which layer will give you the instructions for pushback creation, and here you can pick whether to use polylines, surfaces, or solids. You define how constraints will apply inside or outside a contour of solid, above or below the topography. All these constraints can serve to include or exclude zones, and you can mix several if you need it. Plus, you can decide whether to consider the connections between blocks calculated for angles or ignore them, which would include all blocks within the constraints. You set it up for each pushback. For instance, we've used polylines for all of our manual pushbacks. It's fine if the lines cross over each other, blocks won't count it twice, but if you're a perfectionist, you can make each new contour touch the last one, and that works too. So let's check out what we've got. The first pushback matches the contour exactly. The second extends from the west and adds depth because we're considering block connections. The third from the east is an extension of the first at the top and deepens the previous 2. The working areas at the top are exactly where we set them. Let's look at the frames resulting from pushback construction. Displaying them from largest to smallest shows the mining sequence based on our pushback designs. Just like with final contours for pushbacks, you can explore graphs and detailed tables, and notice how we've aimed for each pushback contain nearly the same amount of ore. This is something you can achieve with several tries, even when doing pushbacks manually. We won't go into each detail, but let's quickly see how these pushbacks relate to each other. And the ore quantity is kept consistent, and each pushback follows the last. And it's interesting to note that with more pushbacks, the first one gets smaller, speeding up the initial ore extraction, which is crucial at the project start. For example, now we're looking at the project with 7 pushbacks. The first pushback is at the richest part of the deposit. Then the development heads south, expanding west and east over time. Each pushback is a unique set of blocks adjacent in time. I should mention how user-friendly this plugin is. Strategic planning isn't easy, so we've tried to make it as straightforward as possible. And you see, with the minimal settings, you get highly flexible and customizable outcomes. It's all step-by-step, making it hard to get lost. Wrapping up how to create pushbacks in K-Mine, it's worth noting that besides fully automatic and manual methods, there is this hybrid approach that Bright was talking about. It's like auto mode, but with some manual tweaking. So you start an automatic pushback and then apply 1, 2, 3, or as many restrictions you need to refine your pushbacks. This gives you a maximum flexibility and customization in the process. For example, within the pushback restrictions, you might specify one of the wireframes that show the optimization calculation result. Then you set the target parameters for finding all subsequent pushbacks, and the calculation kicks off once you start building the second pushback, with the first one being set according to your restrictions. So you see that out of 3 pushbacks, 2 were automatically generated and 1 was manually set using wireframe. And this approach is great if you want to know exactly how you want to begin, but there are still things to figure out the next steps. And the icing of the cake when creating pushback is definitely the dynamic design plugin that is part of our design model. If you're after the most realistic plan, your calendar schedule should include pushbacks that you design. Now let's see how to make a pushback project using just a wireframe. First, draw a contour where you want to get ISO lines aligned with the level list. Use the create ISO objects command to generate ISO lines you need. Then pick out the lines you want to work with. Further, in our case, it should be lower and unique, not repeating the previous elevation. Smooth them out for easier work, and then we move to the fun part. We make a list of levels, which is super easy with automatic filling, and you just need to know your pit specifications. Then we decide which baselines belong to which level. If a line isn't at its assigned level, we project it onto that level. Then we start building the edges. We add one row, then another, turns, connections, and so on to make sure every part of the pit is accessible. Each section of the project must be mineable. This must be ensured at the design stage of the final pit contour, and all approaching roads must be interconnected to ensure flexibility in the transportation of materials. Then we introduce the topography into the project and recalculate. This shows us which lines are above the ground level, which is crucial because our project must intersect with the topography to work correctly. The plugin has various visualization tools to make this process as clear as possible. And once everything is set and looks good, we construct the final wireframe. This combines two wireframes, the project and the added initial topography. In just 2 minutes, you can have a project for the final pit's contour, pushback, and other pit elements. Sure, sometimes you'll need more time, but it's much faster than manually designing bench by bench. And this plugin isn't just for quarries, you can use it for designing dumps too. So to wrap up, here's a sneak peek for the next update. Our dynamic design model now includes volume calculation functionality done in the most user-friendly and quick way possible. And you can calculate volumes considering level lists, which make document preparation just a breeze. Plus, we'll soon add the ability to visualize the part of the block model that's being calculated. So let's dive into calendar planning. First of all, our schedule model is great for long-term, mid-term, or short-term planning. Its strength is in how easy it is to use and how much you can customize it. The plugin lets you calculate mining sequences either automatically or by hand. We've set up 5 scenarios with different numbers of pushbacks. To keep it real, I'll say up front that these calendar plans aren't perfect, and that's the point, to show what actually happens with different pushback counts. All site parameters are the same across all scenarios to avoid skewing the results. And to achieve our goal, it's enough to run the calendar plans in auto mode. The target for ore is constant, but overburden varies because of pushback size differences. We've set a hypothetical pit productivity limit of 30 million tons of rock mass per year. For ore, we're looking at 7.2 million tons annually over 12 years of operation. Once calculated, we get sets of blocks showing the mining schedule over the development method. Towards the end, we'll lower production to reflect a more realistic scenario. We suggest using wireframes for outputs similar to pushbacks, where you can load and display them sequentially to see the development timeline. The core of planning here is to open one pushback, mine it, and then move on to the next at the right time. So let's look at the results for a scenario with 4 pushbacks. Just looking at the extraction blocks won't give us much insight, so we'll soon switch to a more detailed table analysis. So for a quick example, here's a manual calculation. We're using 2 excavators. One stays on a site until it's fully mined out before moving, and while other shifts in a bit earlier to set up the next work front. After manual calculation, we've prepped schedules to help make further planning decisions. And with manual calculations, you can monitor where the mining phase is each day of your plan, and regardless of the planning intervals. Manual planning also opens up additional features like calculating the transport distances for rock mass. So now let's get into analyzing the data from our planning process. The key takeaway here is that the fewer the pushbacks, the harder it is to reach the ore because you're dealing with a lot of more overburden. Sure, you can smooth out the volumes over time and start on the next pushback sooner, but with 3 pushbacks, we see some big spikes in overburden that might not be achievable. Because the ore targets are met only from the 4th interval. With all that overburden early, there is a dip in the net present value, and we used economic indicators similar to those in our deposit optimization project. So with 4 pushbacks, there is still some excess, but there are spikes there, but the spikes are not as high as the NPV improves a bit. The schedule starts to look more doable, suggesting that with more time we can average out the workload. When we plan with 5 pushbacks, the spikes are even less pronounced. The NPV is higher, and everything seems to be going according to plan. Likely by moving some overburden earlier, we can tackle these issues. Planning for 6 pushbacks shows a pattern of progressively reducing overburden volumes. This is a good sign that spending more time in early development stages could boost the NPV. The spikes are smaller and the NPV is better. When we have 7 pushbacks, the overburden volumes are pretty stable, no big swings, since each pushback is smaller with more of them. It looks promising with the highest NPV, but the real-world feasibility might be a different story, more related to pushback design. Finally, we look at the graph focusing on NPV, which clearly reflects the economic impact of long-term planning. As expected, fewer pushbacks mean a lower NPV, and more pushbacks mean a higher one, and we've discussed why this happens. It's also worth noting that adding 1 more pushback after the 6 doesn't significantly affect the NPV, but adds complexity to the design, possibly make it unfeasible. So considering all factors, it seems 6 pushbacks is like the sweet spot for these conditions. If not possible, 5 pushbacks could work with extra focus on early development stages. Here another slide that is worth tuning into the streams for. We've tried to sum up the key points about what happens when you have too many pushbacks, although our analysis shows that more pushbacks can be beneficial. Now, what's good for higher number of pushbacks is bad for fewer number of pushbacks, and vice versa. So here's the deal. Smaller pushbacks get worked through quicker, leading to more excavator moves, which can reduce potential productivity. More roads mean higher construction costs and more time spent. Another big issue is that with smaller pushbacks, you might run into unexpected problems like stability issues or geological surprises, which could halt the process and hurt profitability for a while. Narrow pushbacks mean higher risks. On the positive side, it's easier to plan and execute mining with more pushbacks, and the relatively smaller overburden allows for working on multiple pushbacks at once if needed. Projects with more pushbacks tend to be more economically attractive, and as you can see, each point we've discussed has an impact whether on the economy or on the risk of executing the plan. So what affects the size of pushback? First of all, it's the size of the deposit. The bigger it is, the larger you can make your pushbacks. Then there is the size of your mining and transport equipment. It's wise to make the pushback width multiple of several working areas of the equipment you'll use. Of course, you've got to consider the stripping ratio and how much mineral of the right quality you need. The amount of exposed mineral should keep the plant running smoothly and give you time to open up the next side. So here are some tried and true pieces of advice from our team on choosing pushback size. Each pushback should start at the pit surface and go down to its maximum depth, with the bottom aimed squarely at the mineral. So the only exception might be when switching mining methods where the part of the pit is already developed. The width of the pushback should be between 2 or 5 working area widths of your equipment. So we recommend going for 3 or 4. This depends on your equipment size though and the pit scale. The range isn't huge, so feel free to experiment. And one crucial rule: each pushback should be an extension of the one before it. So the only time you might break this rule if the mineral deposit is uneven or patchy, where stripping one part might be more efficient than starting a new section. Use these tips and remember, the goal is to start developing each pushback as late as possible, but reach the mineral as quickly as possible. That's the secret to successful scheduling when using pushbacks. All right, so to sum up what we've covered today and how to apply it. First, every deposit has its own quirks. So each one needs unique strategy, but there are some general guidelines you can follow that will help you with the strategic planning across the board. Take advantage of the benefits that different pushback widths offer when they make sense for your situation, but always be mindful of potential downsides. Then, when it comes to calendar planning, using pushbacks usually yields better outcomes and improves its value. So, also, no mining operation can succeed without the right people to carry out these strategies. So, please be mindful of that. So, good luck, everyone. I hope today's stream has given you something useful and proves helpful down the line. I'll see you next time.